line trip. So let me just sort of plug in that a little bit more. Was that analysis of the chest X-ray at 37,000 feet? Was that just an analysis at that altitude, or is that take into account the attenuation of the fuselage of the aircraft?
That's a great question. That's for North America in particular. That's kind of the average dose that you get if you're flying commercially, you know, at 37,000 feet for 10 hours. But that is only from the, as we were just mentioning earlier, from IMAP stuff. That's only from the galactic cosmic rays.
Right, right. So that's cosmic, not the CMEs and what.
That's right. If there's
so I was going to ask how that's affected by carbon fiber aircraft fuselage now, which are coming into vogue with the big super.
Yeah. So basically, it doesn't make a difference. The issue is that the really energetic particles come in, and even if we coated the planes with lead, okay, which the airlines wouldn't want us to do, but
there's a penalty for that.
That's right. The more energetic particles would still make it through. They create a spray of lower energy stuff, and it's that soup that we're actually embedded in.
So that goes to the CMEs, then there's no Faraday cage available to us. Or,
that's right.
Okay.
Yeah.
So also in your testimony, you said 1990 NORAD lost 200 satellites. Did they lose them permanently or temporarily?
No, but that's a good point. So there's a fence, a space surveillance fence, a radar fence, that the objects are coming through, and if they don't come through at a certain time, they had to go and look for other objects. Well, as it turns out, 200 of them from the big density changes from that big geomagnetic storm caused the satellites to have their orbits changed such they didn't come through the fence at the right time. So they had to go off looking for other objects. But now a new object came through. They didn't know if it was a missile, or they didn't know if it was an old object that had been delayed in its orbit. So that was a big deal to lose.
They've sort of misplaced these 200.
Yeah, right. They did find them there, but it took a lot of work on their part. Yeah.
They just lost track of them.
Exactly, right. They lost track of them, yeah.
Thank you for that clarification. I was worried we were going to have to replace every single satellite. So what steps do we take to harden our satellites these days, now that we know this? I guess that's a Dr. Gibson question maybe, huh?
Technical steps? I think you need to, I would first answer that you need to figure out exactly how bad it could be, and that's this benchmarking activity, to say how bad is it going to be if it's a Carrington storm, or could it be even worse? Because there's the question of, you know, we've only got 100 or so years of experience with this, and how bad might it be in the future? And there's been studies, for example, looking at other stars, looking at records on the moon, in ice cores, to try to get in a sense of how bad the radiation could be, and it could even be worse than anything we've experienced or the Carrington storm. So that's the first step, is to get that climatology, to get that benchmarking. And then in terms of the technical hardening, that's outside my wheelhouse. I don't know if Kent wants to.
So I would just respond a little bit from the technical side as NASA builds its spacecraft, which are science and providing fundamental understanding. Nevertheless, they have to survive in space and have to survive these storms. And so understanding how parts, electronic parts that sit on boards, electronic boards, how they respond to that environment, how different materials degrade over time. All of these things are part of really understanding our space environment and space.
You're actually launching a probe into the sun, or right near the sun. Yeah, so what are you doing to harden that one?
Oh, that is a major accomplishment. The big issue there, as you can imagine, is temperature, right? And so there was a significant effort focused on the heat shield that provides, it's going so close to the sun, but yet right behind that heat shield, it's a nice warm, 80 degrees Fahrenheit or something like that. It's amazing what they've done. So that's a temperature thing, but nevertheless, think of the same thing in terms of radiation environment, how to protect those parts, the components.
The charged, highly energetic charged particles. Right. Can you give me a hint what you're doing?
Well, so I'm not a parts person, but I just know that they do spot shield them with some heavier elements, lead and titanium and those sorts of things.
So you're a great time manager. You've cleverly, we've run out of time again. I want to get the answer to that.
Sorry about that.
I yield back, Mr. Chairman.
All right, thank you. Very, very fascinating. I'd like to